Hello and welcome to the Design Day video for our project, the Design, Build, Fly Aircraft Design Competition, also known as DBF. Our sponsor is the American Institute of Aeronautics and Astronautics, and our advisors are Dr. Sergey Shakaryev and Dr. Jikan Thanga. Our team members are Roman Gonzalez, Sydney Kilen, George Stancu, Davis Goolsby, Matthew Banko, and Michael Debbins. As set by AIAA, the objective for the 2021 DBF competition is for a team of engineering students to design, construct, and test an unmanned aerial vehicle with a towed sensor. The aircraft must be capable of executing 3 different flight missions and a ground mission. The first mission is the staging flight, the second mission is the delivery flight, where the aircraft must fly the course with the full payload, and the third mission is the sensor flight, where the aircraft must fly as many laps of the course as possible and remotely deploy and retract a towed sensor. The ground mission is a ground demonstration where the selected team members load and unload the Mission 2 and Mission 3 payloads, as well as demonstrate the functionality of the payload components and aircraft control surfaces. For each mission, the aircraft must take off within 100 feet. All missions are timed and require the aircraft to fly as fast as possible with a competitive yet feasible payload configuration. The heavier or larger the payload components are, the more competitive the configuration is.
In designing the wing, we chose from a selection of airfoils that seemed to offer the qualities we wanted. Each one was analyzed using simulation software to get lift and drag curves and were directly compared. Based on both its CL alpha curve and lift-to-drag ratio, the team chose the Clark Y airfoil. For the wing's plan form, we used the same simulation software to analyze the finite wing lift-to-drag ratio of a range of taper geometries. By varying the taper ratio and taper length, the sweet spot was found that maximizes lift-to-drag.
The control surfaces themselves were oversized to make sure we had enough control authority with our projected flight speed. Given that our aircraft was constructed to optimize payload carrying capabilities, our flight speeds were relatively low, requiring larger control surfaces. A stability analysis was also conducted to determine the aircraft's neutral point in order to find a range that our center of gravity could rest. We felt most comfortable with a static margin between 5 and 20% based on pilot input and previous year's competitions. So tail sizing was completed with an X-flyer, since that's essentially a prerequisite in order to develop numbers for both static margin and center of gravity. Different lateral and longitudinal dynamic flight modes were also investigated, along with time response curves to show that the aircraft would return to equilibrium when subjected to outside forces, like say a gust of wind.
For our landing gear for the DBF plane, we went the tricycle configuration with one single steerable nose gear. For the payload for Mission 2, it's a heavy lift aircraft capability where we have to be able to carry multiple sensor shipping containers inside the cargo bay of the aircraft. For Mission 3, we must be able to deploy and recover our deployable sensor out of the end of the aircraft. During flight, the sensor must turn on and off a set of 3 flashing LED lights that is pre-programmed into the sensor.
The role of the structure system was to provide an effective yet lightweight backbone to the aircraft, supporting not only all various components but making reservations for certain subsystems because of competition optimizations. The large rectangular cross-section of the aircraft is a byproduct of this, intended to maximize Mission 2 payload capacity while also affording us the room for the batteries and deployment and recovery mechanism.
Our first foam prototype was flown lighter than intended due to the fact that one of our 2 flight batteries were missing as a result of shipping delays. This issue forced us to change the layout of the internal components of the aircraft and forced us to fly lighter than intended, which resulted in an increased static margin, causing our aircraft to be too nose heavy. Despite this, we decided to proceed with flying because we had an important deadline rapidly approaching. However, this decision ultimately resulted in a nose-down crash 28 seconds after takeoff, where the aircraft dove 60 feet at full throttle. This crash totaled the aircraft and provided us with minimal useful flight data. COVID-19 was one of the biggest challenges we faced as a team. One of the most effective ways to validate design decisions for this project is to iteratively prototype. In past years, DBF teams have had the luxury of spending ample amounts of time in lab to collaborate and construct. The pandemic made it extremely difficult to meet in person safely. Workdays had to be scheduled far in advance, and they were constantly being rescheduled and postponed due to unforeseen shipping delays.
Originally, the final design of the aircraft was to have full balsa wing and full balsa body construction. To allow more flexibility during testing and allow for greater resilience between flight tests, our initial prototype would be a foam construction. With all that said, as a team, we had to take a step back to acknowledge some truths about our current situation. Let's start with one of the bigger ones. Balsa construction is not easy. While the team wanted to fully realize the capabilities of our design, we realized this was a goal that was only possible if we made our design more realistic and more achievable. Instead, we optimized for a foam prototype to be our final design. A solid balsa spar was used to reinforce the wing, which would normally be weak without it. Additionally, we had basswood plates installed at the front of the fuselage where strength was necessary. While not as strong as our original full balsa construction, this modified prototype allowed us to have a resilient and easily adaptable prototype that would withstand the rigors of flight testing.
In terms of landing gear and payload, we encountered several problems this year. For the landing gear, the L-shaped configuration kept deforming and was unable to control the aircraft. To resolve this, we switched to an upside-down H configuration, which allowed for greater control and better stability of the aircraft. For the payload, the original winch system was underpowered and inconsistent, which we resolved by 3D printing a new spool for consistency and redirecting the power draw from the auxiliary batteries to the main flight batteries to solve the real performance issue. In addition, we were able to prove that the light system within the payload sensor worked and was able to be turned on and off using the transmitter within the aircraft.
After the first crash, the electronic speed controller, which controls the main motor, was irreparably broken, and thus we quickly had to diagnose the issue, realize that the speed controller was broken, and quickly order a new one before we could perform a second test flight.
After all that was done, we contacted our pilot to schedule another flight test. Except, of course, it turned out that he was out of state and would be gone for a month. After a bit of panic over who would fly our plane, one of our team suggested an RC pilot he knew. Thankfully, the new pilot agreed to help, and we avoided a major roadblock.
While performing our final checklist, we noticed one of our aileron servos wasn't working. It had somehow burned out. We had backup servos in the event something like this occurred, but when replacing them, we discovered that they had problems of their own as well. With no other options, we were ready to call it a day and head back empty-handed once again. That was when someone passing by noticed our dilemma and offered up 2 of his servos. We integrated and tested them and they worked perfectly, and our flight test was saved.
Our prototype was both able to fly and we were able to deploy and utilize the payload system.
Our team had the unique experience of building an RC airplane from scratch during a global pandemic. Despite facing many unprecedented challenges, we came together and created a successful project. We all learned so much, both as individuals and as a team. We really enjoyed this project and we hope you did too. Thank you.